Alrighty, good morning. Creature apparently also wishes us a good morning. Okay. So, let's go ahead and get started. We're going to do a practice problem or two to start. And then let's look at another one. Alrighty, so remember we kind of have three IMFs that we're going to be looking at mostly. And so there's really only one question that we need to answer first, which is, are these things polar or not? Right? Because that's going to give us a lot of information right off the bat. So if we're looking at PCl3, we know right away it can do London. That's a given. Everything does it. So throw it on there. Is there a possibility for hydrogen bonding here? I hope not, because there's no hydrogen in this molecule, so that'd be quite silly for us to say hydrogen bonding. So we're good there. We're going to get a big old X for that one. Nope, no hydrogen bonding. And so we have to think, can we get dipole with this? And so that's that question that we need to figure out if it's polar or not. And so we should do the Lewis structure. We're going to see that this is 5 plus 21, 26 electrons. Phosphorus, bunch of chlorines. And so we're going to have used 6 of them. We have 20 left. There's another 18. 2 left. There we go. So is this guy going to be polar or not? What do we think? For sure polar. Right? This thing gives it away. But we could technically check if we wanted to. But lone pair is, again, kind of our like indicator that it's going to be a polar molecule. There are polar molecules that don't have lone pairs, like we looked at chloroform, but the fact that this one has a lone pair already tells us that it's polar, so we don't really need to think about anything else. So this can undergo dipole-dipole interactions. So we would say that PCl3, phosphorus trichloride, can undergo these two forces with each, if there's a second one nearby. Alright, CCl4, just for time, we have done this Lewis structure before. Of course, London, for sure. Again, we do not have hydrogens in this molecule, so it would be quite silly for us to say hydrogen bonding. And so now we just have to look and see if this thing is going to be polar or not. And what do we think? What do we think about carbon tetrachloride? Yeah, not polar, for sure. So we're going to have another big ol' X on the dipole. Because, again, carbon tetrachloride is not polar. So just remember this is... This one, London can be anything, so either polar or non-polar. Dipole is only for polar things. And hydrogen bond is for polar things with a H on one of those three elements. Okay. So do we have any questions on that? Because after that, then we're going to talk about the consequences of this. Like, what's the whole point? And so we're going to see that today. Okay. In that case, let's go ahead and move on. One thing that we are going to point up or deal with first, the consequences of our intermolecular forces here. So, let me see. Okay. We're going to see that there's something in chemistry that's always fundamental to us, is that it takes energy to break bonds. So, we've already talked about how polar things want to be with polar things, non-polar things want to be with non-polar things. It's because of this as well. And so we're going to see that even though these forces aren't like covalent bonds, they're still bonds. So, I mean, that's why we have or these interactions are bonds, kind of. So, for us, it's the same as saying these interactions. We're going to see that we've already kind of talked about this, but covalent bonds are going to be much stronger than H bonds, which are stronger than dipole interactions, and then London forces. So we know that this is the strongest and these are weak. So remember, these three are technically interactions. They're not like bonds as we talk about them, but these covalent bonds are much, much stronger. So that being said, it's easier to break these interactions apart than it is to break apart covalent molecules. So that being said, if it takes energy to break bonds, let's see, what color haven't I used? To break a strong bond, we need a lot of energy. However, to break a weak bond, we need a little energy. And so we're going to see kind of how these things work out. So let's go ahead and look at some things. Consider some phase changes. So we know our three states of matter that we typically talk about. What do we think? So we remember drawing like kind of structures of what these look like. If we were to kind of right here, well, you can do it here again. Why not? Okay. I'm gonna just draw some water molecules. All right, and then of course we have our liquid where they're kind of sloshing about. And we have our gas state. Okay. So if we look at these, which one of these does it look like we're going to have kind of the strongest or the best interactions going on within? Just looking at them. Or it may in fact be easier for us to answer the opposite. Which one of these do we think has, like, there's really not any interaction whatsoever? In fact, this may be easier for me. Yeah, right. I may be able to find better pictures on Google because I'm a crappy artist when it comes to this. Okay, let's see if we can't find some nice, pretty... Aha! Okay. Oh, even better. Okay. So I'm going to pop up on our Google here because thank goodness. So if we go ahead and look at what these are looking like, this is a pretty good example right here, actually. We can see the ice. All these molecules are really nicely arranged. And in fact, they're going to really be kind of maximizing their interactions. And as we see with this liquid water here, kind of on this side, since it's less organized, we're going to be still having nice interactions, but since things are moving around each other, that those interactions are kind of just, forming and breaking and forming and breaking again. Whereas, as Lamonda has said, in the gas state, things are just moving so fast that they're not even really interacting with each other at all. Like they just don't have time because they're moving so quick. And so, let's see. Let's go back to this one. So we're going to see that solids result from strong intermolecular forces, and gases result from weak intermolecular forces. And so we're going to see that, of course, temperature is going to play a big role in what state of matter things are. But if we want to just kind of level the playing field and think about them at 0 degrees or 25 degrees Celsius or whichever temperature we want, this is going to be the trend. So the stronger your intermolecular forces are, the more likely you are to be a solid. Whereas the weaker your intermolecular forces are, the more likely you are to be a liquid. I'm sorry, a gas. Or a liquid. I mean, liquids are kind of in the middle, right? So they're kind of medium intermolecular forces. So we can compare a few things. C4H10 and C5H12. Okay. Let's take a look at these, a little like table here we're going to come up with. And then let's see. Let's go ahead and also look at their molar mass, and then we'll talk about that. So, water, of course, at room temperature is a liquid. We know that. It turns out that all these guys are gases up until pentane, 5 carbons, pentane, where it is a liquid at room temperature. But it boils at like 35 degrees Celsius or something. So it's a low boiling point liquid. And then the molar mass of water we know is 18-ish. For methane, it's 16. Ethane is going to be 24, 30. And then 36 plus 8 is 44. 56. No, 58. And then... So I want you to think about why I'm doing the molar mass, by the way, while I do my elementary calculations. And so we're not really going to care about these like kind of middle areas. We're looking at this stuff right here. Who cares about the middle stuff? But if we look at these, we notice that water is a liquid, even though it has a quite low molar mass, actually. But pentane, which is also a liquid, but barely, has a molar mass that's much higher than water. And so we're going to see that because water has hydrogen bonding, it is much harder, or what we can also say is it takes more energy to break to turn it into a gas. So the water molecules, they want to be near each other, right? They interact nicely with each other. We have the positive hydrogens interacting with negative oxygens, partial of course, and that's a favorable thing. It's good. They like it. And so we're going to see that it requires... Water is actually a really special molecule. It requires a tremendous amount of energy to turn into a gas. But if we look at this pentane molecule here, the C5H12, even though it has a much higher molar mass, it's still going to be a liquid, but barely. So it's a much easier liquid to boil. And so the point of all this is to illustrate that, remember that London forces depend on your number of electrons, right? The more electrons you have, the stronger your London forces become. We're going to see we need way more electrons in our system to be able to kind of outmatch hydrogen bonding. So we can think like we're going to keep, adding carbons and hydrogens onto these hydrocarbons. And so it's probably going to be when we get to like octane or nonane, where we have molar masses that are above 100, so tons of electrons in there, before they have roughly the same boiling point as water. So this is just illustrating for us the physical reason why we have water as a liquid. Because it has these super strong intermolecular forces, those forces want to kind of hang around together. They are attracting each other. And so it's going to take a lot of energy to make them move fast enough so that they can kind of break those interactions. So at some point, it turns out it's roughly 100 degrees for water. at that point, it has the water molecules have enough energy to kind of break apart from each other. They're moving so fast that it becomes less favorable for them to slow down and interact than it is for them to just leave. And so that's the reason for this. So this whole little chart here just illustrating that even though we have quite many more electrons in pentane, it's still nothing compared to water with its hydrogen bonding. So that's the idea here. So eventually, the London forces will win out when we have so many electrons going on. You know, if we have, how many electrons does this have? 5 times 6 plus 12. So there's 42 electrons in... No, I don't know how to count. I don't know how to count, guys. But there's a lot of electrons in pentane. Water has, let's see. Water has 10 electrons total. Whereas pentane has, I can do this, 5 times 6. 30 plus 12. 42. Okay, pentane has 42 electrons. Water has 10. So even 4 times the number of electrons, it's still nothing compared to the hydrogen bonding. So eventually they'll win once we get into, you know, C10H whatever it's going to be, 22 I guess. But that's the reason. So the whole point of all this is that your strong IMFs will result in a high boiling point. And so eventually, once we have enough electrons with our hydrocarbons there, they will become solids at room temperature. It's definitely something that will happen, but or rather, there'll be liquids with higher boiling points. And so that's the idea here: is that the stronger your IMFs are, the higher your boiling point is going to be. All right, and again, because it takes energy remember, we have happy interactions happening to go from that to this. So to go from a liquid to a gas, that's boiling, takes a lot of energy for it to happen. Takes more energy for it to happen if you have strong forces. All right, does that kind of make sense? So these water molecules want to hang around together. So if you want them to break apart, you gotta make them crazy. Gotta give them plenty of energy. Speaking of which, since we have to put in energy for this to happen, we have a word for that. We would call this something that is a process that is endothermic. Endothermic means that it requires energy to be absorbed. So this liquid water has to absorb energy in order for it to turn into a gas. We know that, right? If we wanted to boil our water, we would put it on the stove, right? And we would crank up the heat and wait 10 minutes. And lo and behold, eventually our water starts to boil. We have to put in energy. That's what endothermic means. In order for this thing to happen, we have to give it energy. Okay, or we could throw it in the microwave, whatever. Again, we'd be zapping it with energy. So whatever way you're trying to boil your water, you got to put energy in to do it. Just so we have the other term here, the opposite of boiling is condensing. and that's a gas turning into a liquid, is exothermic, which means energy is released. So in order for a gas to become a liquid, it has to get rid of some energy before it can turn back into a liquid. So either that's going to be a temperature change or whatever. This is why steam burns are not so good, because the steam wants to become back to a liquid again. And so it's going to say, oh, look, there's your hand. I'm going to dump all my extra energy into your hand. And as a result, I'll be able to turn back into a liquid. And that's why steam burns are kind of worse than just boiling water. If someone spills boiling water on you, it's not as bad as if they were to zap you with an equivalent amount of steam. So there we go. So in your horror movies or whatever, or your foundry working conditions or wherever you are encountering steam things, steam burns are much worse than just regular boiling scalds. So fun. Okay, cool. So we're going to see that we actually have the same idea happening if we go from... I'm not going to draw the hydrogens anymore. I'm just going to kind of draw the molecules like this, just because interest of time, right? Alrighty. So what do these states of matter look like? Perhaps it's hard to see, but let's say that this might make it a little bit easier for us. We're going to assume these are pretty close together. This is liquid going to solid, right? This process, of course, we know is called freezing. And so freezing is liquid going to solid. Sorry, not gas. And so if we look at it, we're seeing that we have a liquid which is moving around, and the forces, the hydrogen bonds are kind of breaking and reforming. Whereas in the solid case, our hydrogen bonds are stuck. They are permanent. Well, kind of permanent. For as long as it's a solid, I guess. They're permanent, right? We're going to see that this process is going to be kind of the opposite of gas. So we saw liquid turning into gas, where the gases were far apart. We broke our bonds between the water molecules. In this case, we're going to make our bonds even more sturdy. And so it's going to be the opposite process, right? So instead of having to give it energy to break the bonds, we're actually going to be making more bonds. We're going to make them stronger. And that's going to be the opposite. So freezing will be an exothermic process. So we are going to be kicking out energy. And so if we want to think about it, so remember, one measure of kinetic energy is temperature, right? So temperature is one of our kind of ways to measure the energy of something. And so if we think about it, if we make something lower in temperature, that's making it lower in kinetic energy. We know that in order for us to freeze our ice or water into ice cubes, we have to put it in the freezer, right? And the freezer is colder than the outside. And so we're going to have to we're going to have to kind of take away the energy. So if we put something in the freezer is going to absorb its energy. It's going to take away the energy from our water. And as a result, we're going to freeze our solid. Okay, so freezing actually will release energy. And lo and behold, we're going to have the opposite situation here. If we want something to melt, let's say we have some butter or chocolate or whatever. If we want our butter or chocolate to melt, we have to heat it up, right? If we heat it up, we are giving it energy. And so melting is going to be the opposite, is going to be endothermic. Ooh, how shame on me. I have forgotten a... what is that? Particle? No, determinant. There we go. Grammar. Hooray. Wait a second. I seem to have frozen. Let's see. I can't tell if I've frozen for you guys. No? Okay. So, well, this has stopped, like... Okay, then let's just try and fix this one. Huh. Okay, there we go. Maybe this will work. Yes. Okay, let's see if this is any better. Okay, cool. I had written the word "and" in there, and I was like, it's not showing up. Okay, so we're good now. Awesome. So does this kind of make sense? I think the easiest two to remember are the endothermic ones. If we remember, boiling and melting are both endothermic. Those might be the easiest ones for us to relate to real life because those kind of make the most sense. Like if you want something to melt, you have to give it heat. You have to light your candle on fire for it to melt. If you want to boil something, you put it on the stove, you have to turn on the heat. Let it boil. So if you can remember the endothermic ones, the exothermic ones are just the opposite process. So opposite of boiling is condensing, and the opposite of melting is freezing. So so long as we can remember those, we'll be good. One other thing to note is that the heat required to melt something is equal to the heat released when something freezes. So the amount of heat, which we describe by this term delta H. Delta H is technically called enthalpy. Oh my gosh. We have a fun word for that, but that for us, that's just the change in heat. So the delta H for melting is going to be the same as the delta H for freezing. So the amount of heat we need to put into our butter to melt it is the same amount of energy that would be released if we were to try and freeze it again. So these processes are just kind of the opposite. And so we're going to see that they're actually going to have the opposite sign mathematically. So we have a convention for this. We're going to say that this one, the melting one, is positive, and the freezing one is negative. We describe this actually, we can describe it in words. That anything endothermic will have a positive change in heat. If we think about that, that's saying that we are, remember, for endothermic things, we have to give them extra heat. And so, have we talked about delta in this class? We might not have. Someone remind me. Have we talked about? Have we done any math with delta yet? Like this capital delta, that is. No. Okay. Well then, I'll talk about that. So delta. Okay. My apologies. It's getting ahead of myself here. So delta is the same thing as saying change in. So whenever you see this triangle in chemistry or physics or whatever, or math even, that always means the change in something. So we're saying these are a change of heat. So that's always saying that it's whatever your final, in this case heat, would be, minus your initial, how do I spell initial? Yeah, that looks good. Your final heat minus your initial heat. So that means that delta H is your final heat minus your initial heat. And while we're not really going to calculate anything with this delta H, or at least these H's initial, H final, H initial, we can think about it in terms of, the energy we started with. And so we have to consider, if we think about an endothermic process, we are giving it heat, right? That's so if we want to boil the water, by the time the water boils, it has more heat, right? We've given it more. So for an endothermic process, that's telling us that it has more energy at the end. Once we've put in all that heat, it now has more heat. If you want to think of it as kind of like a bank vault or something, if we put in money, we have more money than we had before. That's what this is saying. And so that's why it is positive for an endothermic process. So anytime we have something that's endothermic, our delta H will be positive. And so that, therefore, the delta H is going to be negative for an exothermic process. All right, so exothermic processes release energy, right? And so again, if we think of it as a bank vault, if the bank is releasing your money to someone, uh, shame on them, that means we have less money than we started with, right? If the bank has released the money to someone else, we have lost money. We have less than we have before. The change is negative. Right? Does that kind of make sense? Alrighty. So, oops. Delta H is usually in units of energy over quantity, which means for us that could be joules over grams, or joules over moles, or kilojoules over kilograms, or whatever. Something that has a unit of energy at the top, that's joules for us. Or we might see calories, that's another unit of energy, over some sort of unit of quantity, whether it's going to be grams or milligrams or moles, some amount of something. And so this tells us delta H is a conversion factor. That will allow us to go between energy and quantity of something. So if I were to tell you that the delta H for vaporization, that's the same thing as boiling, was negative 44. Three dots just mean like therefore. I think. I've never really. Let's find out. To the Google. Okay, so it is generally used before a logical consequence. So it is the therefore sign, apparently. So there we go. Oh, have I done it right? Oh no, upright triangle. Okay, yeah, then we're good. So apparently that comes from math, but it means therefore. So we're saying delta H is a conversion factor because of the fact that it has 2 units, right? Something that has 2 units is going to be a conversion factor. So this number tells us the energy, required to boil 1 mole of water. So it is a conversion factor. So, awesome. So we can actually use this information. We could say, how much energy does it take to boil 218 moles of water, if we're given this number. So, of course, you would never memorize these constants. They would be given to you, or you would calculate it with the amount of, or whatever's given to you. But this is one of the two equations we're going to have in this chapter. So we're going to have one about this delta H idea, and then we're going to have another one later on. So we're looking for how much energy it takes, let's just say in kilojoules. And we know that it's going to, our delta H for vaporization, for boiling that is given to us as negative 44.0 kilojoules per mole. So if we look at that, we're always going to start our unit conversions with our the quantity that we're given in the problem, right? A measured quantity. And so if we look about it, we have negative 44 on one side, and we have 1 mole on the other side. Which one are we going to put on the bottom here? And which one's going to go on top? I'll just duplicate it down here. Yeah, we need moles to cancel out, right? So we'll put 1 mole on the bottom, negative 44 kilojoules on top. And let's go ahead and do that math. 218 times negative 44 is going to be negative 9,590 kilojoules. Wait, did I put the sign wrong? Boiling is endothermic. I'm sorry, I put the sign wrong. I apologize. This one is positive. All these fixes I have to do. My apologies. Yeah. Since this is an endothermic process, it should be positive. So that's my mistake. I gave you the wrong one. Okay, so if we look at this number then tells us we need to put in that much energy to boil all the water. Okay, so that's what that's telling us. So we are able to kind of calculate that, which is awesome. So what I was illustrating before, so this case it's going to be 44 kilojoules per mole. Turns out for the opposite process, that's where we're going to have the negative one. So it's the exact same amount of energy that would be required to condense all that steam, but it would actually then give off energy instead of take it in. So since boiling and condensing are opposite processes, and therefore their delta H is the same number but opposite sign. So technically I could have given you the delta H for condensing. By the way, this is typically combined as just saying they typically just give it as delta H VAP for vaporization. And they will usually just give you, who's they? I will usually just give you the number. And so it's kind of, you will have to kind of keep in your mind that if it's an endothermic thing that's happening like boiling is, you just keep the sign the same. But if you're going to be doing the opposite of it, you would switch the sign. Okay, let me find another one for you here. I have to actually look up the numbers because I don't want to teach you the wrong numbers. Oh, forget it. I'll just make one up. Okay. We have another delta H that's for the opposite one, or for the other one rather, not the opposite. And let's say it's kind of making the number up. It is smaller than vaporization, but I'm making this one up. It's probably not accurate, but that's okay. We'll be able to see it work. So it turns out fusion is the word for freezing and melting. So I guess I can write that out. You'll also this is delta H fusion. Which is abbreviated FUS, and that means that it's talking about melting and freezing. So what is the delta H for freezing going to be? Let's look at that. So remember, the delta H fusion here is telling us the number, the magnitude of our conversion factor, but we have to think about the sign here. So is this going to be, is freezing an endothermic process or exothermic? If you want to get something to freeze, do you have to heat it up or cool it down? What do we think? Yeah, it's exothermic, right? And if it's exothermic, that means it has what sign with it? Is exothermic positive or negative? So we would say this is negative 6.7 kilojoules per mole. And since freezing and melting are the opposite, we know the other one is going to be endothermic, and so will be positive for the same number. So this thing is just again illustrating that same process will have the same amount of energy change, but it's just going to have the opposite sign. And if you take 111, you're going to learn more about this sign business later on. Okay, so alrighty, let's just make this one more step. So let's take a 500 ml water bottle, which has 500 grams of water inside of it, and I'm going to freeze it. Alright, so if I'm going to do that, we know freezing is exothermic, it's going to release energy. So let's see if we can calculate the amount of energy. Can we use these numbers directly? Can we just go directly from grams to kilojoules? No, I don't think so. Because it looks like our delta H is given in kilojoules per mole, right? So we're starting with grams, and we want to end up with kilojoules. And so it looks like in this case, we're going to need to do moles in the middle. So sometimes delta H could be given as, joules per gram, which in that case you would just use it as is. But in this case, because it's given to you in kilojoules per mole, we have to deal with the moles then. So how are we going to, what's the conversion factor we're going to use for that? Of course, this one is delta H, right? Delta H converts between moles and kilojoules for this problem. What's the conversion factor for grams to moles? Who remembers that from the nightmares? Or the crying in the shower? Or the crying in bed before the nightmares? Or after? Remember, this guy here is the molar mass, right? So molar mass is how we go from grams to moles. All right, so once again, all we're doing here is conversions. That's all we do in chemistry, unit conversion, over and over and over in different ways. So let's do it. Remember that the molar mass for water is 18 grams per mole. Alright, so since we are out of time, I'll just set this up for us. Grams is going to go on bottom, right? Because we need that to cancel. And since this is freezing, we're going to use the top one, right? Plug it in. Alright, so in doing this, I got negative 100, and I guess we're going to have to say 190 with the sig figs in there. So it's we're gonna release this much energy when we freeze that water bottle. Okay, so looks like we're all out of time for today. So remember, tomorrow we're gonna go over exams. If you want to, if you have questions, like before, go ahead and put pictures of the questions in Discord so we can see them when we go over them tomorrow. We're not gonna, I guess, have homework on this stuff quite yet, or I guess I could put the homework, but it'll be due maybe next week, not this week. So if you want to start working on it, you can, but it's not going to be due this weekend. So just focus on your exam homework. Okay? So if you want, I'll see you all tomorrow, same time. Again, it's optional, just exam review. Otherwise, I'll see you all on Monday. So have a safe and pleasant afternoon, or I don't even know what morning, day. And then maybe I'll see you tomorrow. Okay? So enjoy. See you then.